Hello and welcome to LFI Educates. Today we are going to start this chapter, that is nuclei. In this chapter, you have a major deletion this year. So many things are curtailed. So very few things you are going to study. First thing you are going to study is about composition and size of nucleus. This is the first thing that you will have to study. Then the second thing that you are going to study is about mass energy equivalence. Mass energy equivalence. And this one you already know that mass can be converted into energy using this Einstein's relation E equal to mc square. Then the next thing that you are going to study is about nuclear energy. Nuclear energy. The types of nuclear reaction you study under this. You will study about fusion and fission reactions, nuclear reactions, fission and fusion nuclear reactions. So that's all in this chapter. So more than half is removed from your syllabus for this year. So let us start with this composition of the nucleus. When we say composition of nucleus, inside nucleus what substances that you can find? The elementary particles you can find inside the nucleus are the protons and the neutrons. That is very clear to you. Now this sum of protons and neutrons together we call it as nucleons as well. We call it as nucleons. But beside that, you'll have to know certain things like atomic mass unit. You write it as atomic mass unit. We write it as AMU, or sometimes we write it as unified atomic mass U also. Like this also will be present. Atomic mass unit is 1/12 the mass of carbon 12 isotope. We call this as atomic mass unit. Whenever we talk about the mass of an atom, then we take 1/12 the mass of carbon 12 isotope. Carbon 12 isotope means 6C12 with mass number 12. That mass we call it as atomic mass unit. The next thing you have to know is about atomic number. Atomic number, we generally write it as Z. It is the number of protons or the number of neutrons, protons or the number of electrons present in an atom. Number of protons present in an atom is known as atomic number. Or we can say that number of electrons, because number of protons and number of electrons are equal in an atom, neutral atom. So we can even say number of electrons instead of protons present in an atom is known as its atomic number. We represent with this letter Z. The next thing that you will have to know is about mass number. mass number, that is A, we write. The sum of the number of neutrons and protons is known as mass number. Now atomic number is equal to number of protons, that is Z, plus number of neutrons, that is N. This gives us the mass number. The mass number is denoted by letter A. These are the few things you have to know. The next thing that we'll discuss is about the size of the nucleus. Let us see the size of nucleus. The size of nucleus, we can do like this. If R is the radius of the nucleus, with mass number A, with mass number A, it has been found out by Rutherford in the Rutherford's alpha-ray scattering experiment that the volume of the nucleus, is directly proportional to the mass of the atom. Now when we say mass of an atom, we know that electrons are excluded. Electrons are generally lighter. When you write electron, we write -1e0. That means mass is negligible. It's not 100% zero, it's near to zero, but it is negligible. So the entire mass of the atom is concentrated at the center core of the atom, that is the nucleus. So here the volume of nucleus will be directly proportional to the mass number of the atom, or we can say the mass of the nucleus. The volume of nucleus, volume of sphere, we write as 4 by 3 pi r cube. It is directly proportional to A, and these are constant terms you can see here. If I take here also, it will remain constant, it will become 3 by 4 pi. So I can write r cube is proportional to A, or r is equal to this proportional sign. If you remove it, we use a constant term called r naught. A and r, we take it as r naught a to the power 1 by 3. Or you can remove the power first, make it 1 by 3 before taking r naught. Then it will be r is equal to r is proportional to a to the power 1 by 3. Then if you remove the proportional sign, you can use the constant r naught. It will become like this. You can calculate the radius of the, or the size. Radius means the size of the nucleus with this formula, where r naught is a constant. R naught is a constant called the nuclear unit radius. And its value is r is equal to 1.2 into 10 to the power minus 15 meter. And this 10 to the power minus 15 meter we call this Fermi also. So 1.2 Fermi also you can say the value of r naught. It is constant for all the nucleus, but the size of the nucleus, the radius of the nucleus varies. This order of the nucleus is this one, 1.2 into 10 to the power minus 15 meter. Let us do one small numerical analysis. This r naught is constant, to remain the same, but r will keep on changing depending upon atom to atom. The size of the nucleus may vary slightly, may become more or may become small. Let us do one small numerical. So here is one question. You can see, obtain the approximate value of the radius of a nucleus of uranium 238, 92 uranium, atomic number is 92, mass is 238. take R naught is equal to, if you don't give the value also you should know this value, but it will be given generally. So here atomic mass A is equal to 238. You can see clearly the uranium atom is given. Then what else you require? R naught you require, it's already there. Therefore approximate value of radius you can write this R is equal to R naught A to the power 1 by 3, and put the values. R naught is 1.2 into 10 to the power minus 15 meter. The unit overall will remain as meter only. Atomic mass is 238 to the power 1 by 3. Now cube root, as we know that we cannot calculate, there is no formula for it. So which cube is nearer to this value you have to search. Suppose to say 5 cube is 125, 6 cube is 216, 7 cube is 343. Now this is 6 cube, this is 7 cube. Now which value is closer to 238? 238. Then difference you can find out. 238 and 216. 238, 216. Difference is 2. And here 238 and 243. Difference is 5. Only 5. So this value you will take it. So cube root of 238 you will take around 7 cube. And if you take around 7 cube, the number which is close, then you have to take it and do around 7 cube into 1 by 3. Then 7 2s are 14, 4, 1 in hand. 7 and 7 plus 1 is 8 into 10 to the power minus 15 meter. Like this you can calculate the radius of the nucleus that is given to you. And here already atom given to us is uranium, nucleus of uranium. The radius of nucleus of uranium will come out around this much approximately. Now let us discuss about nuclear density. Nuclear density, when we say, it is the ratio between the mass of the nucleus divided by its volume. Mass by volume gives us density in mechanics. So here also the mass of the nucleus divided by the volume of the nucleus will give us the nuclear density. It is the ratio between mass of nucleus and, or is the ratio between mass of nucleus and its volume. And its volume, it means the nuclear volume. Nuclear density, to calculate it, mass of nucleus, if I write it as Ma, the total mass of the nucleus, divided by volume. I will write down first mass of nucleus divided by its volume, volume of nucleus. We denote it with this symbol rho, the nuclear density. Mass of nucleus, if I write it as m times the mass divided by volume of nucleus 4 by 3 pi r cube. Then this is m into a, this 3 will go up, 4 pi, and r value, as you know, r is equal to r naught a to the power 1 by 3. So r cube, if you do, this will be r naught cube a to the power 3 into 1 by 3, it will become r naught cube a. So r cube will become r naught cube a. So a, if you cancel it out, then you get the formula for nuclear density. 3 times the mass divided by 4 pi the unit nuclear radius cube. This gives us the formula to calculate the nuclear density. But nuclear density is approximately constant for all the atoms. its value is, the value of rho is 2.3 into 10 to the power 17 kg per meter cube. The SI unit of nuclear density is kg per meter cube. So any atom is given to you is approximately, you should get this value only. For any atom, the value is approximately constant. Now let us see about mass energy equivalence. Now mass is equivalent to energy according to Einstein. Whenever any nuclear reaction takes place, a neutron and a proton, when they react, they give us nucleus. To form a nucleus, neutron and protons are there. Now during the combination of neutron and proton, the masses, it says that, suppose I am taking a big value here to make you understand. Suppose it is 1 kg, and proton also it is suppose 1 kg. If you are combining them together, actually the law of conservation of mass says that 1 plus 1, the nucleus must be of 2 kg, but it is never 2 kg, it seems it is 1.9 kg suppose. Like this you get it. This mass, lost mass, how much is lost? Then what you will do is, this 1.9 and here 2. 2 minus 2 means 2.0 minus 1.9, you get 1. This 0.1 kg of mass, it gets converted to energy. We call it as nuclear binding energy. That mass gets converted to energy. Here this is the mass 0.1 kg. This is the mass that will get converted to energy. And this mass is also known as mass defect. Mass defect. Here it was 2 kg, together it is 2 kg, and here it is 1.9 kg. So there is a defect of mass. A difference if you do, you get the defect of mass. We call it as mass defect. And that mass gets converted to energy, and that energy we can calculate with this relation E is equal to mc square. Now we write sometimes in terms of delta M indicates mass defect. That mass defect, how much is the defect in mass? 0.1 kg. Then velocity of light is 3 to 10 to the power 8 meter per second square. If you multiply it, you get the energy. 3 square is 9, 0.9 into 10 to the power 8 2s are 16. In SI unit it will be in joules. So Einstein gave us the formula to calculate the energy, that is mass energy equivalence, that mass, lost mass gets converted to energy, and here delta M is called the mass defect. Now when you do it in practice, actual way if you do mass defect, delta M is equal to mass of proton, ZMP we write, plus mass of neutron, A minus ZMN, minus mass of nucleus. This will give you your mass defect. This is the formula for your mass defect. Now to calculate the energy from mass defect, E is equal to delta mc square using Einstein's relation. Delta M, we write this one ZMP plus A minus Z. You know the letter, I hope. Z is atomic number, A is mass number, mass of neutron minus mass of nucleus. If you multiply with the velocity of light square, you will get the lost energy or the defect mass, that how much it will get converted to energy. How much mass is lost, that will get getting converted to energy in nuclear reaction. And this energy is also sometimes we call it as nuclear binding energy. This energy is called nuclear binding energy, and it is defined like this. the energy with which the protons and neutrons are bound together within the nucleus. That energy is called nuclear binding energy. Let us do one numerical and see with this. So let us calculate this and see. You are asked to find out binding energy per nucleon. You should not get confused. Binding energy is EB. We already know that is delta mc square. And binding energy per nucleon is divided by the mass number. This gives us binding energy per nucleon. So here we'll do like this. The binding energy per nucleon of calcium nucleus, given the mass of calcium, mass of neutron, mass of proton, and you are asked to take one atomic mass unit equal to 931 mega electron volts divided by c square. So what we have to do is, first of all, we have to find out the mass defect, or you can write down the mass of neutron, mass of proton, or how you do mass defect. Let us do mass defect. What is our formula? Write down. It is Z mp plus A minus Z mn minus the mass of the nucleus m. This is your mass defect. We write it as delta m. So Z is how much? Atomic number. When you see there 20. Mass of proton is how much? Mass of proton is this one, into 1.007825 plus A, atomic mass, it is 40, minus atomic number, it is 20, Mn, mass of neutron is 1.008665 atomic mass unit, minus mass of the nucleus for calcium atom, it is this one, 39.962589 atomic mass unit. So you write down like this. So let us calculate here. 2 5s are 10, 0, 1 in hand, 2 is 4 plus 1, 5, 2 8s are 16, 6, 1 in hand, 2 7s are 14, 15, 5, 1 in hand. So this will be 1, 2 zeros are 0, 2 1s are 2, and 1 0 is there. So after decimal 6 digit, it will be 20 point. That is plus here 20 into this value. 2 5s are 10, 0, 1 in hand. 2 6 are 12 plus 1 is 13, 3, 1 in hand. 2 6 are 12 plus 1 is 13, 3, 1 in hand. 2 8s are 16 plus 1 is 17, 7, 1 in hand. 1, 2 zeros are 0, 2 1s are 2. And here also you have 20, in 20 you have 1 0. So 3, 4, 5, 6 is it, minus 39.962589 atomic mass unit. So add it, these two, 20.156500, 20.173300. If you add 0, 0, 8, 9, 12, 2, 1 in hand, 3, 0, 4. Then we'll subtract with this value minus 39. This one we are adding, minus 39.962589. 10 minus 9 is 1, 9 minus 8 is 1, 7 minus 5 is 2, 9 minus 2 is 7, 12 minus 6 is 6, 12 minus 9 is 3, 9 minus 9 is 0, 0. So it is 0.367211 atomic mass unit. Like this, first we'll find out the mass defect. Now to calculate the binding energy, or energy EB is equal to delta mc square, and delta m you got this one 0.367211 atomic mass unit converted into mega electron volt. Then it will be into 931 mega electron volt divided by c square. And here you have one more c square. If you cancel it, then you get the answer in 341.87341 mega electron volt. Then we'll find out the average binding energy. Is equal to binding energy per nucleon. Binding energy we got 341.87344 mega electron volt divided by mass number of calcium is 40. So we'll divide by 40 this value. Three four 1.873441 divided by 40. One time cannot do. 4 7 4 8 32. 32 0 1 2, then 8 bring down, decimal will come. 4 5 20 0 18 7, then 4 4 16 160. You can complete everything or you can leave like it was 8.54 mega electron volt per nucleon. Like this we can represent the answer. Now let us see how do we get nuclear energy. Nuclear energy we get in two ways. There is one that is fusion or fission reaction, and in one case we get during fusion reaction. There are two types of nuclear reaction. In both the cases energy is liberated. Now let us see the first one, that is fission reaction. A fission reaction is that reaction in which a heavy nucleus mass number more than 230, they get broken down into smaller atoms or smaller nuclei, we say, with nearly the equal masses, and during that process energy is liberated. That process of nuclear reaction we call it as fission reaction, and large amount of heat energy will be produced. Whereas in case of fusion reaction, lighter nuclei, they combine together with mass numbers less than 10. They combine together to form a heavier nucleus, and when they become heavy, it becomes stable. The nucleus becomes stable. During that process also energy is released. That energy also we call it as nuclear energy that we get during fission reaction. Now to discuss this fission reaction, there are two types of fission reaction. One is called controlled and one is called uncontrolled fission reaction. In controlled fission reaction, generally we do inside a nuclear reactor to get heat energy, and that heat energy we can convert it into electrical energy. That reaction we call it as controlled nuclear reaction. In controlled nuclear reaction, one neutron or one reaction only will allow it to occur at a time. If we allow many reactions to take place at a time, then that reaction will be called as uncontrolled fission reaction, and such reactions are used to make atom bombs, or we call it as nuclear weapons. And this one, controlled fission reaction, we carry out to get electrical energy, One such fission reaction I'll show you here. When a slow moving neutron is allowed to bombard or to react with uranium-92, uranium-235, then first it will give us uranium-92-236, and this is an unstable nucleus. It gets broken down, it gets split up into barium, with atomic number 56, mass number 141. Then krypton, atomic number is 36 and mass number is 92. And along with that, 3 more neutrons are produced, and a large amount of heat energy. In nuclear physics, we call this as Q value of nuclear reaction also. That gives us the energy due to mass defect. Now here in this case, you can balance it. 0 plus 92 is 92, and here also 56 plus 36 is 92. 3 times 0 is 0, so it is 92. Top 3 ones are 3. 3 plus 92. 92 plus 3 is 95. Plus 141, 236. It should be balanced. The nuclear reaction must be balanced. You can just check it. Then this is one example of fission reaction. Here what happens, one uranium nucleus, when it gets bombarded or gets broken down into pieces, then you can see 3 more neutrons are produced. These 3 more neutrons, if you do not control it, control means how we can control it. These 3 neutrons that are produced here, if they can be made unreactive or paralyzed, then out of 3, if 2 we can make it unparalyzed, only 1 paralyzed, 1 only will remain. Then only 1 reaction will take place again with the second uranium nucleus. If you can do that, then we say it as controlled fission reaction. But if you just leave it straight, then what will happen? These 3 neutrons will react with 3 more uranium nucleus, thereby creating 3 3s are 9 fission reaction. 9 fission reaction means the energy produced will become even more. Again, this 9 will produce 27. It will just go on multiplying like this, and then the amount of heat energy produced will become more and more. This fission reaction is used for warfare purpose. We call it as nuclear weapon. But if you can control it, if you can absorb these 2 neutrons and only leave 1, then only again 1 reaction will take place. Then a limited amount of heat will be produced. Again, next step also, 2 more neutrons if you absorb it, allow only 1 reaction to take place, then only if only 1 reaction takes place, limited amount of energy will be produced. The amount of energy produced in 1 reaction is also enormous. It can produce large amount of electrical energy. It can produces large amount of heat energy. That heat energy can be converted into electrical energy. That is used in controlled fission reaction in nuclear reactors. Now let us see how a nuclear reactor works. This is your shielding. It will be made up of lead, and on outside surface it will be fully concrete with brick walls. These are all brick walls, so that no nuclear radiation will escape out. This is your brick wall. Then these are the 2 ways. From one way you pump liquid sodium. Liquid sodium is used as coolant. When you pump liquid sodium, then to go here, the heat produced in this reactor, here in this reactor you place the uranium fuel like this, blocks of uranium. Then you have control rods. Control rods are made of cadmium or boron. They can absorb the excess neutrons. You can insert it, you can absorb the excess neutrons produced during reaction. Then the heat will be circulated through this way. The liquid sodium, the coolant will cool down the reactor and the heat will come out this way. and while coming out this way, it will pass through a chamber called heat exchanger. Here water will be kept, and when this liquid sodium, hot liquid sodium will pass through this heat exchanger, this is your heat exchanger, then steam will be produced. That steam will go and hit the turbine of the generator and will produce electric current. Suppose this is your generator. Now this liquid sodium will get cooled down while passing through this, and then it will circulate here back. Again the liquid sodium will come here back. Then this water that you have used, the steam, the used up steam after rotating the turbine will be collected back again. The used up steam will gather here in the heat exchanger. Here two circulations will take place. One is the liquid sodium that you are passing it. It will go and boil the water here, heat the water. The water will produce steam. Steam will go and heat the turbine of the generator to produce electric energy. And then the used up steam will get back again into the heat exchanger. There should be one more condenser. There will be one condenser here nearby before coming to the heat exchanger. The steam that will come here will get cooled and then enter inside the heat exchanger. Here water, cold water, you allow it to pass inside, and here hot water will keep on coming out to cool down the steam. So this way nuclear reactor works. First of all, what you do is before placing the uranium, you put the inside the control rods. These are the control rods. These control rods will make sure that there is no neutron inside the reactor core. After you insert it, then you will take it out, and then you have to place graphite here in between the uranium rods. Here graphite moderator is used. Moderator is used. The graphite function, the function of this moderator is to slow down the fast moving neutron. If you trigger a neutron inside, suppose from somewhere you are triggering a neutron, then it will come very fast. So to slow down, suppose if there is a liquid here, sticky liquid is present here, a marble, if you just drop it here, you know that it will move slowly. So like that, here also graphite is filled up, so that the neutron, when you trigger it, it will have to move very slowly. And when slow moving neutron will go and strike the uranium, then only the nuclear reaction will take place. So graphite is used as moderator. After that, the uranium fuels are placed. After placing the uranium fuel, you will trigger the neutron, and then with the help of this control rods, you have to control the 3 neutrons that you have produced in one reaction, 2 to make them ineffective, and only 1 to keep, so that only one reaction takes place at a time. If all the neutrons are not absorbed, if just allowed to react inside the reactor core, then the reactor core will burst out. Such type of thing happened in 1986. You may be knowing about this. This we call it as Chernobyl nuclear disaster. And this one took place in Ukraine, the destruction of the nuclear reactor. And question also has come, it has been asked in your board exams regarding this. do you know or not to know exactly? If the radiations like alpha, beta and gamma rays, these are removed from your syllabus, but you should know that these are the harmful radiations that is to come out from the reactor core if it is not shielded properly. If destruction will take place, this ionizing radiations can affect a large area, or it can destroy a large area. So this is for controlled fission reaction. And uncontrolled, as I said, one reaction will take place, 3 neutrons will produce, 3 reactions will take place next, every 3 will produce 3, 3, 3 will become 9. 9 reactions will take place, then 1 will produce 3, 9, 3, 27 neutrons will be produced. Like it will go on spreading and covering a large area. It will destroy until and unless the whole amount of uranium or the nuclear fuel is vanished. This is only one example. Uranium, plutonium, radium, thorium, these are the radioactive substances that you can use in a reactor core. Now, the next thing that you have to know is about your fusion reaction. The next thing is about your fusion reaction. It is that type of reaction in which the lighter nuclei combines together to form a heavy nucleus, as I have said already. And to undergo this fusion reaction, large amount of heat is required, heat energy is required. Then only the nucleus will undergo a collision and then reaction will occur. Generally, the energy that is produced in stars, that is in sun, according to Hens-Bethe, this is the cycle. We call it as proton cycle. It goes like this. How we get the energy from the sun? The temperature should be, temperature of sun is around 2 into 10 to the power 6 Kelvin of this order. Then only the fusion reaction is possible. Proton cycle, it goes like this. 2 hydrogen nuclei, 1H1 plus 1H1. If it reacts, it gives us 1H2 plus 1 positron plus 1 is 0 plus, you know that energy will be released, right? Sometimes as Q1, E1 also you can use. This deuterium in turn will react with 1 hydrogen atom to give 2 He3, the isotope of helium. Here also energy will be released. Let us mark it as E2. 1 plus 1 is 2, 2 plus 1 is 3. Again, in turn, if one more hydrogen atom reacts with this isotope of helium, then you get a stable helium, that is 2He4. And during that process also, one more positron is produced, plus energy will be released. So overall, if you sum up the reaction that takes place in the sun, how many hydrogen atoms we have? 1H1, 1H1, 2, 3, 4. 4 hydrogen atoms. 1H1, 4 times you have. Then this, you have 1 deuterium and 1 helium. This is 3. 3 plus 1 is 4. Yes, correct. This is helium. Then you get here, these two will get cancelled. Deuterium will get it here. 1H2 plus 2He3 plus 2He4 plus 2 positrons plus 1 E0 plus you have Q1, Q2, Q3, Q1, Q2, Q3. So here if you look, these two quantities, you can cancel it, the equal quantities, and then you get the overall reaction. 4 hydrogen nuclei, if they react, then they give you 1 helium nucleus and 2 positron, and this overall energy, we write it as Q, or we can write it as E. Their Q value is nearly equal to 24.7 megaelectron volt when 4 hydrogen nuclei reacts. Then you get the energy in the sun like this. It is this energy we get from the sun when our Earth faces the sun, according to Hens-Bethe. So with this, we'll come to the end of this chapter, Nuclei. Stay tuned with LFI and have a nice day.